summation on the right hand side. Okay, and then you compare each terms and they are the same. So you can conclude that those two summations are equal. Okay, and I also mentioned that the shorter way is we just change the index. Okay, we shift the index. Okay, for example, you want to show that this is the same as this or this is the same as that, right? So if, for example, you want to shift, okay, you want to make like to make the power equal, right? Because the power here is what is equal to n plus 1, n minus 1. To make it n, power of n, you got to replace this n with n plus 1. So that n plus 1 minus 1 will equal to n. So we shift, right? That's why here, okay, you in order to make the power x plus 1 power of n, you have to change this n on your left hand side with n plus 1. So this will be, you replace n with n plus 1. So you have n plus 1. Whenever you see n, you replace n with plus 1. So n here, so n plus 1. And then n here, n plus 1. And then also n there, n plus 1. Okay, and then you simplify. Okay, so n plus 1 equal to 1. You bring 1 to the right hand side. So become n equal to 1 minus 1 equal to 0. And then this n plus 1 minus 1 equal to an, and then you will get the right hand side of summations, meaning that they are equal. Okay, that one if you want to shift the index, and then you want to rewrite the generic terms, right? For example, here write this series. Okay, so this summation is series actually. You presented in terms of summations, but it is series. Okay, you want to write or you want to convert this series in x power of n. Right? Okay, here this series is x power of n plus 3. You want to change the power, okay, to n. How? So you have to change this n, replace this n with n minus 3. So in order to convert this series in x power of n, you replace this n. Whenever you see n, you got to replace n with n minus 3. And that's why you have n minus 3 there. And then n plus 1 will be n minus 3 plus 1. Okay, an becomes an minus 3. X power of n plus 3 will be x n minus 3 plus 3. Every time, each time, okay, you encounter n, you replace n with n minus 3. Next step, you simplify, right? So bring minus 3 to the right hand, to the left, right of sign of equal sign. So this become n equal to 3. So n minus 3 plus 1 equal to n minus 2. N minus 2. And then here n minus 3 plus 3 becomes x power of n. Okay, so now you convert the series, okay, in x power of n. Okay, all right, the same thing here. Okay, example 3. Okay, before I proceed, is it any questions? If you want to rewrite, if you want to convert from this power to the given power, in this case xn plus 3 to x power of n. Any questions? Any questions so far? No question.
Sir,
Yes.
why we need to minus n minus 3?
Kat sini, okay. Rewrite the series summation n from 0 to infinity n plus 1 an times x power of n plus 3 in x power of n. Here the given power is xn plus 3. Now we have to convert this into power of x power of n. Okay, and that's why we need to replace this n with n minus 3, so that n minus 3 plus 3 will becomes what? X power of n. Boleh tak?
Boleh.
Okay, sebab sekarang kalau macam ni, kalau ini dia katakan sini n power n x power n plus 1. Okay, that mean kalau we want to change this from x power of n plus 3 to x power n plus 1, so we need to replace this n with what?
N plus 1.
Okay, kalau kita nak convert this series, the asal dia x power of n plus 3, dan nak convert dia kepada x power of n plus 1, so this n we need replace with what? So that's n plus 1. N minus
Minus
kan?
2. 2, yes.
Okay, so each time you encounter n, you got to replace n with what? N minus 2.
Oh.
Boleh? Kalau sini
Boleh.
kalau kita nak kalau ni contoh sini kita nak macam okay. N. Okay, n minus 1. Okay? So sini kena replace n with what?
Minus 4.
Yes, minus 4. So each time n ni you have to kena replace with n minus 4. Faham tak? Ini pun n minus 4, minus 4. Okay? Macam tu. Okay. Alright, now what is it now? Solution now. Right, this one. Okay. Kat mana saya pergi tadi? Saya kena ni balik. Okay, now I kena pergi. Let me see. Okay, shifting. Okay. Now rewrite generic terms. Okay, kita dah buat macam tu. Okay, example 3. Okay, example 3. Okay. Write, okay, this summation or this series, okay, we have two series there, all right, summations n from 2 until infinity, n times n minus 1, cn x to the power of n minus 2, plus summations, okay, n from 0 up till infinity, cn x n plus 1. Okay, write this as one power series. Okay, like these two series as one power series. Okay, so now you have to decide, okay, which power that you want to convert to. Okay, so this is in this example, I convert everything to x power of n. Okay, I want to convert everything to x power of n, meaning that, okay, in order to convert both summation into x power of n, this n I will replace with what? N plus 2, while this n I will replace with n minus 1. Okay, we shift the index. We shift, okay, and then, okay, we replace this n with n plus 2, while this n will replace with n minus 1, right? So I replace this n with n plus 2, so that this will be n plus 2 minus 2 will be x power of n. So replace this n with n plus 2, this n with n plus 2, n minus 1 become n plus 2 minus 1. Okay, so cn will be cn plus 2, and then xn will replace with n plus 2 minus 2, while this n we replace with n minus 1. Okay, so n minus 1, and then cn becomes cn minus 1. So xn plus 1 will be x minus n plus 1, right? Next, we simplify. Okay, so you bring to the right hand side, become 2 minus 2 becomes n equal to 0 here, while here n plus 2 minus 1 becomes n plus 1, and then cn plus 2, and then xn plus 2 minus 2 will be x power of n, right? And for these summations, you bring minus 1 to the right hand side, becomes 1, okay, n equal to 1, and then cn minus 1, and then x to the power of n plus power of n minus 1 plus 1 will be x to the power of n. Okay, okay, now the power are the same in both summation, x power of n, and this also x power of n. Okay, then, but we cannot combine yet. Okay, we cannot combine these two summation because what? Because even though the power are the same, but the index are different. Okay, we can only combine two summation if and only if both power are the same and the index are the same as well. Okay, yang ini power are the same but the index is different. This one start with n equal to 0. This one begin with n equal to 1. They are not the same, right? So in order to make this index equal to this, okay, first we substitute, okay, now n we substitute with equal to 0. Okay, so substitute n equal to 0 here. We have what? We have 0 plus 2. That means 2. Okay, and then 0 plus 1 is 1. So that we have this. Okay, so 0 plus 2, we get 2 there. And then 0 plus 1, we have 1. And then replace this n with 0. We have 0 plus 2, we have C2. Now x power of 0. Okay, starting from now on, n we will start with 1. Okay, so n will begin with 1. This when n equal to 0, the rest when n equal to 1 until infinity. So now everything else the same except now n start with 1. Okay, you don't have to do anything for the second summation, remain as it is. Okay, so you simplify this. 2 times 1 give you 2. C2 x power of 0 equal to 1. Okay, so you have 2C2. Okay, okay, if you refer to this summation, now the index in both summation are the same, which is x power of n, and the index are the same as well. Now both index start with n equal to 1. Okay, so we can combine. Okay, we just combine here. Okay, we combine the coefficient of x power of n here will be n plus 1 times n, n plus 2 times n plus 1, cn plus 2, okay, and then plus, okay, plus these, okay, this coefficient which is cn minus 1, everything you times x power of n. Okay, you can combine these two. Okay, you add those coefficients. The coefficient of this, it will be n plus 2 times n plus 1 and times cn plus 2, while this coefficient will be plus, this because it is plus, so plus, okay, cn minus 1, and we multiply all those coefficient with x power of n. Okay, clear tak? Siapa tak boleh follow? Because this is the basic concept. Correct? Later on, you will find these coefficients. Any question before I proceed? Any questions? Okay, so now we write these two summation as one summation only. Okay, as one power series. We only have here one power series. Before this, we have two power series. Now becomes one power series. Okay, the basic concept is in order to combine two power series or three power series, you have to ensure that The power are the same, and also the index must be the same. Okay, then only you can combine. Okay, otherwise you cannot combine those two or three summations, right? So two conditions must be satisfied. The power must be the same, and the index also must be the same. All right. So having said that, we move on to 4.2. Okay, we want to solve first order ODE using series. Okay, now all the solution must be in series, right? Must be in series. Okay, for example, okay, we learned this from chapter 1, how to solve dy dx minus y equal to 0. Okay, this is what? This is first order ODE. And then we know that this is separable. Okay, so this is first order ODE and it is what? Separable types. Right. Okay, you know that how to solve this. Okay, in chapter 2. You know how to solve this in chapter 2, I think. In chapter 2. Right? You know how to solve this. Okay, but you want to represent the solution differently. I think if I'm not mistaken, the answer for this is equal to C e the power of ex. Okay, C times e to the power of x. Okay, that is the solution for this. Later on, we will do this. Okay, that is the solution. Y equal to C or K e power of x. Okay, but now we don't want to write the solution in that form. We want to represent the solution in terms of series. Okay, assume that. Okay, let's assume that the solution for this is in this series form, in power series. Okay, y is equal to c naught plus c1x plus c2x squared plus c3x cubed and so on, infinite series. And you can represent this series as summations. Okay, they are the same. Summation n goes from 0 up to infinity, cn x power of n. Okay, we assume that this solution exists. Okay, but we don't know what is C0, C1, C2, and C3, and so on. But we know that it is in this form. So our task now is to find the value of C0, C1, C2, and so on. Okay, so we know at the end our solution will be in this form. That's all we know. Okay, now in order to find C0, C1, C2, C3, and so on, okay, first we substitute this y in term of this series, in this power series. Okay, and then to get dy dx, okay, to get dy dx in power series, we got to differentiate this series. Okay, so y equal to c naught plus c1x plus c2x squared plus c3x cubed and so on. So we need to differentiate this y respect to x or y prime. Okay, we differentiate c naught respect to x. C naught is a constant. Differentiate constant respect to x, we have 0. Okay, that's why C naught is not here, disappear, because this one will be 0 if we differentiate this. And then differentiate C1x respect to x, we have C1. Okay, differentiate C2x squared respect to x, we have 2C2x. Okay, and then C3x cubed, we differentiate respect to x, we have 3C3x squared, and so on. Okay, or we can write this in series form or in summation. So we bring n, okay, c n x power of n. Okay, we replace this. Actually, this is equal to 0 here, but this is equal to we see here is equal to, no, not here. You know, okay, so you bring x of n, so you differentiate xn, we got n there, okay, xn there, and then cn remain the same because it's constant, and then they reduce the power by 1. Okay, imagine that this is like the normal way that we differentiate. Okay, bring the power down. Okay, the constant remain unchanged, and then you reduce the power by 1. But notice here now n start from 1 because the first term disappear. Okay, before this n start with 0, but this because this term disappear, now n start with 1. Okay, we start with 1. Okay, so we write y prime, which is the derivative of y in terms of series. So you replace this dy with this series, and then this dy with this series, and then this y in this series. So now we will get, okay, dy dx minus y equal to 0. Okay, so that means this one is dy dx, which is our y prime. We replace with in terms of series minus y. So we replace y with this series, so equal to 0. Okay, now all equation involving summations. All right. Okay, you notice here that you want to find the coefficients, the CNs. All right. How? First, we need to combine these two summations. Okay, we need to combine these two series. Okay, we learned that before. Okay, first, in order to combine these two, the power must be the same. Okay, for example, if you want to change this into x power of n, okay, so you replace this n with n plus 1. So you replace this, and whenever you encounter n, you replace this n with n plus 1. So this become n plus 1 equal to 1. Okay, this one n become n plus 1. Okay, c n becomes c n plus 1. Okay, and then x n minus 1 become x n plus 1 minus 1. The second summation remain unchanged. Okay, remain unchanged. Okay, similarly, you can also convert to x power of n minus 1. In this case, the first summation remain unchanged, but this n you got to replace with n minus 1. Okay, it doesn't matter. The answer will remain the same. Okay, so it's up to you which one you want to change. It's up to your creativity, right? So, for example, if I change this into n, x of n, okay, so I replace this with n plus 1, and then we simplify. Okay, you bring n, this one to the right hand side, it become 1 minus 1 becomes 0. Okay, this n plus 1 become n, okay, and then remain unchanged. So c now, cn plus 1, but this will be n plus 1 minus 1 will be x power of n. Okay, now both series have the same power, x power of n, and also we see that both summation also start with the same subscript with the same index. Okay, so this one start with 0, since the power start with the same power and index start the same. So we can combine this. Okay, we can combine this. So the coefficient for this is n plus 1 times cn minus 1 plus 1, and minus because of this. So minus these coefficients minus cn, everything times x power of n, so equal to 0. Okay, and this will be 0 if and only if all coefficient which becomes 0. Okay, this will be 0 if and only if all the coefficients, which is n plus 1 times cn plus 1 minus cn equal to 0. Okay, for n equal to 0, 2, and so on. Why n equal to 0? Because of this index, right? This index. But n start with 0. That's why here n start with 0. And then we add the index up till infinity. And that's why we put 1, 2, 3, and blah, blah, blah. Right? So the index must, the coefficient must be 0 for all, for n start with 0, for n equal to 0, 1, 2, and so on. Okay. Now we want to construct the relationship between these coefficients. Okay. In this case, I want to express. Okay, I want to express Cn plus 1 in terms of Cn. Okay, since n plus 1 times Cn plus 1 minus Cn equal to 0, all right? So n plus 1 times Cn plus 1 is equal to Cn. I bring Cn to the right hand side, become plus Cn. And then this one is n plus 1 Cn. So Cn will be Cn plus 1 will be Cn over n plus 1. Okay, so Cn plus 1 will be Cn over n plus 1 for n equal to 0, 1, 2, and so on. Okay, now to get the value of Cn, okay, for n equal to 0 here, when n equal to 0, so C0 plus 1, that means C1 will be C0 or C0, okay, C0 over 1. Okay, so you replace n equal to 0 into here. So you have C1 equal to C0 over 0 plus 1 equal to 1. So C0 over 1 equal to C0. Okay, C1 equal to C0. Okay, we need to replace n with 1 and several value so that we can see the pattern. Okay, when n equal to 1, okay, now C1 plus 1 becomes C2, and then n equal to 1, so we have C1, okay, over 1 plus 1 will be 2, okay, that means we have C1 plus 2, but C1, for the previous calculation, C1 equal to C0, so you replace this C1 with C0. So now C0 also depend, C2 also depend on C0. Okay, so C2 equal to C0 over 2. To get C3, we replace n with 2. So we have C2 plus 1, C3 equal to C2 over 2 plus 1. That means C2 over C3. But C2, we have found C2 before. C2 equal to C0 over 2, right? So we replace this C2 with C0 over 2. We simplify this. So C0 over 2 times 3. Okay, so we have C0, okay, C0 over 2 times 3. Okay, do for C3, for n equal to 3. When n equal to 3, now we have C4 equal to C3 over 3 plus 1, C4. Okay, so C4 equal to C3 over 4. But C3 equal to C0 over 2 times 3. So replace this C3 with C0 over 2 times 3. Simplify this, we have C0 over 2 plus 2 times 3 plus 4. Okay, and then if you observe this carefully, C0 over 2 times 3 will be what? Will be C0 over 3 factorial. Okay, this one will be C0 over 2 times 3 times 4. This one will be C0 over 4 factorial. Okay, this is the same as C0. I copy here. Okay, over 3 factorial. While this is equal to C0 over 4 factorial. Okay, so 2 times 3 equal to 2. Okay, 3 times 2 equal to 3 times 2 times 1. Okay, we times 1 there, remain unchanged, 3 factorial. This is equal to 4 times 3 times 2 times 1. Okay, so this is 4 factorial. Okay, so we see some pattern here. Okay, when n equal to 2, we have c naught over 3 factorial. Actually, this one should be, no, this one should be, okay, 2 factorial. No, this one should be n plus 1 factorial. Okay, so we see some pattern here. This one should be n plus. Did I make some mistake here? Oh, n. C3 factorial n equal to 1. Okay, here Cn equal to n, 1, T1, Cn equal to 1, 1, 2, okay. Okay, so, okay, the solution will be this. Yeah, I need to change this. So this one will be not 2, this one, okay. Now, we know that solution will be in this form, C0 plus C1x plus C2x squared plus C3x cubed, and so on. Okay, so on. So this one will be C0. Okay, and then you replace C1. Oh, no, it's correct. This one's correct. I'm wrong. Okay, this one will be, okay, now, C2, okay, C2 will be C0 over 2. Okay, so this means C0 over 2 factorial. Okay, this one will be copy here. This one will be C0 C0, okay, 2 factorial, because 2 equal to 2 times 1. 2 times 1 is 2 factorial. Okay, now C2, when we have C2 there, we have C0 over 2 factorial. We have C3 there, C3 equal to C0 over 3 factorial. C4 equal to C0 over 4 factorial. Okay, from this we can conclude that Cn will be C0 over n factorial. Okay, C4, 4 factorial, C3, 3 factorial, so Cn will be C0 over n factorial. So this is the general form. Okay, general form for Cn. Okay, we know that the solution is in this form. Why? Because we assumed before this is the solution will be in this form. Now you got to replace C0, C1, C2, and C3, and so on. Okay, so now we replace, okay, now we replace C1. C1 equal to C0. Okay, so you replace this C1 with C0. Okay, C2, you replace C2 with C0 over 2 factorial. Okay, C3 with C0 over 3 factorial. C4 with C0 over 4 factorial up till, okay, Cn with C0 over n factorial x power of n. Okay, so plus blah 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 until you know that this, or the common term is what? The common term is C0. Take C0 out. Okay, take C0 out. Okay, and then so we have what? We have, okay, 1, because to get C0 we multiply C0 with 1. To get the second term we times C0 with x, and then here with 1 over 2 factorial. Okay, here with 1 over 3 factorial. For this one we multiply C0 with 1 over 4 factorial, and this one will be 1 over n factorial, and so on. But you can represent this series in terms of summations. Okay, so equal to C0 times summation of x power of n over n factorial. How you get this one? You get this one from these common terms. Okay, this one. Okay, you can write in this, right? So this equal to summation n from 0 up to infinity x power of n over n factorial. Okay, when n equal to 0, we have x of 0 which is equal to 1. 0 factorial is equal to 1. Remember, 0 factorial is equal to 1 by definitions. So when n equal to 1, we have x of 1 divided by 1 is equal to 1. So we have this second term. When n equal to 2, we have this third term and so on. And also, you know that from your calculus 2, okay, summation n goes from 0 up to infinity xn over n factorial is equal to what? Is equal to e power of x. Okay, this e power of x. Okay, e power of x can be represented as this power series, and this power series is what? Is Taylor's polynomial. Okay, so how can we get this? Okay, how can we represent ex in terms of Taylor's expansion? Okay, we have done this before in the beginning, in the very beginning. Okay, I think I have given you this. Let's say here. Okay, so here is equal to summation n from 0 up to infinity kxn over n factorial. Okay, this is for sines. Okay, this is for cosines. How to get this? We use Taylor's expansion. You learn that in calculus 2. Okay, in your calculus 2. Okay, so this one is what in terms of solution in series is equivalent to this. All right. Okay, now recall the method you learned in chapter 2. As I mentioned earlier, this is what? This is first order ODE separable. Okay, so how to solve this? Okay, we separate x and y. We bring y to the right hand side. Okay, that means d. Okay, and then here we separate them. So we have dy over y equal to dx, right? When we have dy here, there is free from x. When we have dx here, free from y. And then we integrate both sides. Okay, dy over y equal to 1 over y dy. Integrate this, we get what? You get ln y. Integrate dx respect to x, we have x plus c. Okay, now we simplify this. You use the property of exponent. So we e ln x, it becomes y. E ln y equal to y. So e power of x plus c becomes e power x plus c, or it becomes e power of x. Okay, now because some of you guys make careless mistake, okay, in your first test. This is equal to e power of c, e power of x times e power of c. Okay, this. But in your first test, some of you guys put like this, which is wrong. Okay, this is wrong. Should be like multiply. Okay, so this equal to e power of c is equal to k. That means k times e power of x. So that is the solution that you learn in chapter 2, and this is in chapter 4. Okay, even though the format are different, but they are representing the same thing. Okay, as I show here. Okay, this is equal to this constant times Cex. This one also constant times Cx. The answer are the same, but in different form. Okay, the answer are not different. The answer are the same, but in different form. Okay, so whatever it is, you need to convert that to combine this. Okay, and then right, and then the coefficient must be equal to 0 for this value of n. This value come from these summations, right, from 0, and then you need to establish the relationship between these coefficients, and then you find some terms, okay, some few terms for coefficients, so that you can see some patterns. Then after this, you replace all these C1, C2, and Cn so far with the coefficient that you obtain here, and then you factor out the common terms, and then we will get the solutions. Okay, you get the solutions, right? So that is involving first order ODE, right? All right, now we move on. Okay, unless you have questions, otherwise I will proceed. Okay, with 4.3. Okay, 4.3, we will extend this procedure, okay, this method, to find the solutions for second order homogeneous linear differential equations. Okay, which is in this form. Okay, which in this form. Okay, this is second order linear homogeneous differential equations. Okay, the first step, okay, the first step, we need to rewrite this. Okay, rewrite the given the general formula for second order homogeneous linear ODE into this form. We have to make sure that the leading coefficient is equal to 1. Okay, so in order to make the leading coefficient is equal to 1, we divide all term with a naught x. Okay, divide all term with a naught x. So this will be d square y dx square plus a1x divided by a naught x dy dx, and then plus a2x divided by a naught x, okay, times y, okay, equal to 0. Okay, 0 divided by a naught x is equal to 0. Okay, so from here, from this form, okay, we rename this. Okay, a1x over a naught x, we call it p1x. Okay, p1x is equal to a1x over a naught x, while p2x equal to a2x divided by a naught x. Okay, so now this one will be, okay, this one will be this. Okay, copy here. It becomes, this will be, okay, P1. Okay, this one will be P2. Okay, this will be like this. Okay, be like this. Okay, now, okay, definitions. Okay, there are few definitions that you must be familiar with. Okay, the first definition is analytic. Okay, what do you mean by analytic? Okay, a function f is said to be analytic at x naught. Okay, if, okay, we can represent this function as Taylor's series. Okay, if it Taylor series about x naught exists and converge to f naught for all x in some open interval excluding x naught. Okay, what do you mean by in some open interval excluding x naught? So this is what? This is interval of convergence. Okay, this is interval of convergence. Right? It's converged to f naught, fx. That means what? That means fx can be written as this Taylor series. Okay, and we expand about x naught. Okay, you learned that in calculus 2 there is one powerful theorem that say that every continuous and differentiable function can be written as Taylor series, right? So if that function can be written as Taylor series about x naught, then the function is said to be analytic x naught. Okay, so the first term is analytic. Okay, the second term is what? Ordinary and singular points. Okay, what are ordinary and singular points? Okay, so the point x naught. Okay, we're talking about x naught. The point x naught is an ordinary point of the differential equations if both P1 and P2. So what are P1, P2? P1 is equal to this. Okay, that means A1 over x naught. Okay, and when P2 equal to A2x over A naught x. Okay, if both P1 and P2 are analytic x naught. Okay, the point x naught is an ordinary point of the given differential equations if both P1 and P2 are analytic. Must be both. Okay, if either one is not analytic, then this is no longer ordinary points. Okay, if it is not analytic, okay, now if x naught is not analytic, then x naught is known as singular points. Okay, if not analytics, or if not ordinary, now x naught is called called singular point. Singular point. In other words, okay, if x naught is an ordinary point of the given differential equations, then we can express fx as Taylor series about x naught. Okay, so you need to go back and digest this definition. What is analytic? What is ordinary? What is singular? Singular means it's not ordinary. Opposite of ordinary is singular. All right. Ordinary when what? When the function is analytic at x naught. In this case, both P1 and P2. P1 and P2 are functions. Okay. Okay. Example 4. Okay. Let's see example 4. Okay. Find singular and ordinary points, if any, in the given differential equations. Okay. Number 1, a x squared minus 1 y double primes, okay, plus 2y primes plus 6y equal to 0. Okay. I asked you to do this before, but we will do it again. Okay. First, you need to make sure that the leading coefficient of y double prime must becomes 1, must equal to 1. So whatever you divide all terms with whatever coefficient of y double primes. In this case, x squared minus 1. So divide all terms with y x squared minus 1. So this becomes y double prime plus 2 over x squared minus 1 y primes, okay, plus 6 over x squared minus 1 y equal to 0. So this is your P1x. Okay, P1x equal to 2 over x squared minus 1, and then your P2x equal to 6 over x squared minus 1. Okay, so in order, okay, focus on P1. Okay, and then these, okay, these P1 will be singular, okay, or it will be undefined if and only if the denominator is equal to 0. Okay, this P1 will be undefined if and only if, okay, the denominator is equal to 0. That means x squared minus 1 equal to 0. Okay, imply that x minus 1 times x plus 1 equal to 0. Okay, meaning that x equal to plus minus 1. Okay, plus minus 1. Okay, when x equal to plus minus 1, the numerator becomes 0. When this becomes 0, P1 is undefined, and this point is called singular points. Okay, singular points. That means that this point will make this function undefined. Okay, in this case, x equal to plus minus 1. Those are singular points. Okay, but when x is not equal to plus minus 1, they are ordinary points. Okay, the ordinary points, right? So this is singular point, the point that make this function undefined. Okay, other than this, the points are called ordinary points. Okay, you can do that also for B and also D. This is straightforward. So divide all terms with x squared minus 2. In this case, you divide all terms with 2n minus t squared minus 1 minus 2. And then you simplify. This one you cannot simplify anymore. Right. Now, so we're talking about ordinary points. Okay, 4.3.3, we're talking about we want to find the solutions about ordinary points x naught. Okay, where in 4.3.4, we want to find the series solution about what? About singular point. Okay. Okay, now we focus on series solutions about ordinary points x naught. Okay, now example 5. Okay, determine a series solution for differential equation y double prime plus y about x naught. Okay, y double prime plus y about x naught, about x equal to x naught. So again, okay, before this, we we assume that in this, okay, what equal to this Cn, okay, n power of, okay, before this we replace x naught with 0, okay, and that's why we have x power of n. Okay, so this is a special kinds of Taylor series, we call it Maclaurin series. Okay, Maclaurin series is a special type of Taylor series when we expand about x equal to 0, special case. But from now on, we assume x naught is not necessarily equal to 0. It can be any other value, and that's why here okay, solution will be x power of x naught, okay, x minus x naught power of n, because now x naught is not necessarily equal to 0. This is general form. Okay, that one is special case. This one is general form. Okay, so this is series, power series. So we assume that solution will be in this form. Okay, Cn times x minus x naught power of n. Okay, the same thing as we done before. We differentiate y, we have y primes. So bring n to the right hand, we bring n down, we have n times Cn. Then x minus x naught reduced by 1. And then now the index now change. Okay, okay, but this one, okay, when you replace with 0, we have 0 here. That's why I start with 1. Okay, so equal to, you start n with equal to 1. Right? The same thing here, right? Second derivative, that means we differentiate y prime 1 more times. So you bring n minus 1 in front. So n times n minus 1. Cn remain unchanged, reduced by 1. But now they shift the index. Index now becomes, you start with 2. They are equivalent. Okay, but this one, why you want to start from 0, whereas we can start from 2. Okay, when n equal to 0, this term will be 0. When n equal to 1, this term also equal to 0. And that's why we start with 2. Okay, there's 2 there. Okay, so we repeat the same process. Whenever you see y double prime, you replace with this series. Whenever we see y, we replace with this series. Okay, so y double prime plus y will be, okay, in series, this is y double prime plus y in terms of series equal to 0. We apply the same procedure. we want to combine these two series. Okay, let's say we want to change this n minus 2 into n. Okay, or you can also change this n to n minus 2, or you can change n minus 2 to n plus 1, and you have to change this as well to n plus 1. Okay, the main concept is they must have the same power. Okay, but now I want only to change this n minus 2 to n. So every time I see n, I replace n with n plus 2. So here n plus 2 equal to 2. So n become n plus 2, n minus 1 become n plus 2 minus 1, cn become cn plus 2, x minus 0, x 0, and then this n will be n plus 2 minus 2. Then we simplify this. So this one become n start with 0, bring to the right hand side become 0. So n plus 2 and then n plus 2 minus 1 become n plus 1. Then cn, x minus x naught, n plus 2 minus 2 become n. So x minus x naught power of n. Okay, this one remain unchanged. Now you see that the power are the same and the index is also the same. So we can combine these two summations. So it becomes, okay, n plus 2 times n plus 1 times cn. Okay, we have that one. And the coefficient for this plus, okay, plus cn. And then we multiply all these coefficient with x minus x naught power of n. So become 0. Okay, this series becomes 0 if and only if the coefficient equal to 0. Okay, meaning that n plus 2 times n plus 1 cn plus cn, okay, times cn plus 2 plus cn must equal to 0 for n from 0. From here, n from 0, 1, and so on. Okay, this the next step. Okay, we want to establish the relationship between cn plus 2 and cn. So cn plus 2 from here is equal to minus cn over n plus 2 times n plus 1 for n equal to 0, 1, 2, and so on. So you replace n with 0, you got c2 equal to minus c naught over 2 times 1, okay, which equal to minus c naught over 2. Okay, when n equal to 1, C3 is equal to, you have C3, so C3 is equal to minus C1 over 1 plus 2 equal to 3 times 1 plus 1 equal to 2. Okay, this equal to minus C1 over, okay, over 3 factorial. Okay, we cannot replace this C1 because here there is no C1 there. Okay, C2 depend on C0 and then C3 depend on C1. And when n equal to 2, okay, C4 will be minus C2 over, okay, over 2 plus 2 is 4 times 1, 2 times plus 1 is equal to 3. Okay, so equal to minus, but C2, we have found C2 before, C2 equal to minus C0 over 2 here. Okay, so we over 4 times 3, this one will be C0 over 2 times over 4 times 3 times 2. So this one equal to 4 factorial. Okay, when n equal to 5, so C5 equal to minus C3 over 4, 5 times 4, you will replace C3 with this. Okay, with 3 factorial. Okay, with this, but this is 3 factorial. Okay, so it becomes, okay, minus C1 over equal to minus become plus. The same thing here, minus become plus. So plus C1 over 5 times 4 times 3 times 2. This is the same as C1 over 5 factorial. Okay, for n equal to 4, you will find that C5 equal to minus C6 over 6 factorial. And for C equal to n equal to 5, C7 equal to minus C1 over 7 factorial. All right. So now you can see some pattern here. Okay. when n is when here when the when even for the even case C2, C4, C6 and so on. Okay, so C3 here uh, this C even depend on C naught. When C even depend on C naught, while when C odd depend on C1. Okay, C3 depend on C1, C5 depend on C1, C7 depend on C1. Okay, next step, okay, we expand this term, so this becomes C naught plus C1 x minus x naught. Okay, we expand this term, and then now you start replacing. Okay, replacing all the coefficient. Okay, C naught remain as it is, C1 remain as it is. Okay, because everything depend on C naught and C1. And then C2 now, C2 depend on C naught equal to minus C naught over 2. Okay, C3 equal to minus C1 over C over 3 factorial. Okay, this one equal to 2 factorial. Okay, 2 factorial. And then C4 equal to C naught over 4 factorial. Before this minus now become plus. Okay. And then plus C1 over 5 factorial. So you replace C5 with this. C6 equal now become minus 6 C naught over 6 factorial. And then C7 will be minus C1 over 7 factorial and so on. Okay. And now you can divide this expression into two. Okay. First, the terms that depend on C naught, and the other term, the other equation depend on C1. Okay. So for C naught, the first term, third term, okay, fifth term, seventh term, and so on. So you will C naught times 1 give you this one, and then minus 1 over 2 factorial. Okay, so equal to this. Okay, and then this one become plus. Okay, plus 1 over 4 factorial times this, and plus also 6. Okay, minus 1 over 6 factorial times this. Okay, and the other one, C1 depend on C1, so C1 times x naught minus x naught, and then minus 1 over 3 factorial give you this term, and then minus, okay, and then plus 1 over 5 factorial, you get this term, and then minus 1 over 7 factorial times x minus x naught power of 7. Okay, and then you can write, okay, you can write this series as these summations. You know that this one plus minus plus minus plus minus, it is alternating series. So that's why you have minus 1 power of n. Okay, this is alternating series. Okay, and then this one you can write as this. Okay, C naught at time summation from 0 up to infinity minus 1 power of n. Okay, this one 1 over 2n factorial, because we have 2, 4, 6, 8, and so on. So this one will be 2n factorial, even, right? 2n factorial. And then x minus x naught 2 power of n, because now you have power of 2, 4, and so on. So 2 factorial, 2 power of 2 times n. Okay, okay, this one students have problems to come up with this summation. You need a lot of practice. Okay, you need to review your calculus too. Okay, while this one you can also observe that this also alternating series. You have plus minus plus minus, and that's why we have minus 1 power of n there. All right, because we have plus minus plus minus. Okay, you don't have to, if you put 2n there, always positive, right? This one you have alternating series to the power of n. And then this one, okay, over 2n plus 1 factorial, because this one is give you odd numbers. Okay, you have this one. And then, of course, also you have odd powers. So 2n plus 1. You know that, you recall from your calculus 2, and also from the method you learn in, okay, All right, so this one actually equal to what? Cos x. Okay, this one is actually is equal cos x. Okay, you can represent cos x as this series, and this is equal to sin x. Actually, this is equal to C0 cos x plus C1 sin x. Okay, in order to show this, okay, let's recall the method you learned in chapter 3. Okay, we're dealing with homogeneous second order. Okay, y double prime plus y equal to 0. Okay, you need to change this into what? Into characteristic equations. This becomes r squared plus 1 equal to 0. That means r now equal to plus minus I. Okay, because alpha is equal to 0 there. Okay, beta is equal to 1. Okay, and then it is our solution. Okay, alpha e alpha x, so alpha is equal to 0, and that's why we have e equal to 0 there. So we have 1 there. This is equal to 1. Okay, and then c1 cos delta alpha, beta is equal to 1. That's why we have c1 cos x plus c2 sines beta x, but beta is equal to 1. That's why we have sines x. So now we have this. Okay, e of 0x, which is equal to 1. 1 times c1 cos x plus c2 sines x. So you have c1 cos x, c2 sines x. They are the same, except, okay, different parameters, different variable, but they are the same. So this one will be c0 cos x, c1 sines x. Okay, if you use chapter 3, you get this. If you use chapter 4, you get this. But they are different form, but they are the same actually. Okay, so in chapter 4, all answer must be in terms of series. Okay, well, in chapter 4, in terms of the function, is not in this series form, but if you compare, they are actually the same. Okay, I ask you also to do example 6 and 7. Okay, and then for example 6, okay, we have this. Okay, this is for example 6, we cannot come up with the general terms. Okay, so in that case, you just put dot dot dot. Okay, we cannot get like in example 5, we can write like this. Okay, this series. But in example 6, we cannot come up with general terms, but that's okay. We just write like this. Okay, in example 7, okay, we just need to find the first 4 terms. All right, at the end, we will get this, the first 4 non-zero terms. Okay, I will explain this in the next meeting. Okay, and have you checked your email, your Gmail? Have you checked your Gmail? Did you get your test back? Anyone can respond? Did you check your email?
Yes.
Did you get your test back?
Yes.
Okay, I will. Okay, probably next week or next week, I will show you the scheme. Okay, if there is some mistake, if I got it wrong, okay, if you got it wrong, if you got it right, but I give you wrong, you can also inform me during that period. Okay, but now I just want to focus on your syllabus. But before end of this semester, we will have these kind of sessions. I will share with you all the scheme. Okay, during that period, you have the opportunity or chance, okay, to make some complaint or to inform me if there is any error. All right, so we meet again, and also during this weekend, hopefully I can upload your second group assignment.